Hi friends, welcome back to our channel. In this video, I'm going to teach you two important topics which are related to probability theory. Those are total probability theorem and Bayes theorem. Most of the students get fear about these two topics, but if you watch this video till end, uh, you will be uh, get clear understanding about these two topics: total probability theorem and Bayes theorem. So before we start our discussion about total probability theorem and Bayes theorem, so if you have not seen my previous video, do watch. Why? Because in the total probability theorem, uh, we are going to make use of one of the axioms of probability. So do watch the previous video, that is probability introduced through axioms, relative frequency, and joint and conditional probability. So this video is of only 10 minutes of duration. So please go through this video. And now in this video, we'll discuss about two important theorems, that is total probability theorem and Bayes theorem. If you understand first one, that is total probability theorem statement and proof, it will be easy for you to understand Bayes theorem statement and proof. So let us start our discussion. The starting concept, first topic, that is total probability theorem. Okay, so this is statement about total probability theorem. So just I'll read it one time. The statement of total probability theorem. You go through this statement at least for two times. If you understand the statement, it will be easy for you to do the proof for this theorem, that is mathematical proof of total probability theorem. Let us start this. Consider a sample space S that has n mutually exclusive events. So we are going to consider a sample space. Within that there are n mutually exclusive events. So you need to know what actually a mutual exclusive events is, and such that Bm intersection Bn is equal to 5. That is, if I'm going to take two events Bm and Bn, the intersection about these two events is results to a null set for m is equal to 1 to 3 so on n. Next sentence is the probability of any event A. So within this sample space, if I'm going to define a event A, and if at all I'm interested to find the probability of the event A, which can be expressed in terms of conditional probabilities of event Bn, so which are already present in the sample space. So this is called this probability finding of this probability with respect to, or in terms of conditional probabilities of event Bn, is known as total probability of event A. The mathematical expression is P of A. Total probability of A is equal to summation n is equal to 1 to capital N, P of A given Bn into P of Bn. So this is the mathematical expression which we are going to solve in our proof, and we need to get this mathematical expression for total probability theorem. So for better understanding, I'll make use of whiteboard so that you get a clear understanding about this proof. Once you understand this proof, it will be easy for you to go through the Bayes theorem statement and proof. Okay, friends. Now I'll explain the proof for total probability theorem. So just we'll revise the statement. That is, in order to prove this mathematical expression of total probability theorem, we know that as we have considered a sample space, yes. So I'm going to draw here. It is a sample spaces. So which has n mutually exclusive events. So we have n mutually exclusive events B1, B2, so on Bn. So mutually exclusive events such that Bm intersection Bn results in null set. So here B1 is one event, B2 is one event, B3 is one event, and Bn is one event. So these are mutually exclusive events, right? So we know that if I'm going to
take the union of all these events, n is equal to 1 to capital N, Bn. So what it results? So you can see this, the total sum of all the events results to sample space. So this is equal to sample space. So first we have whatever the data that is given in the statement, we have written n mutual exclusive events. The sample space consists of n mutual exclusive events, and all the events are mutual exclusive events. And next is the summation of all the events leads to sample space. So I hope you understand up to here. Next is I'm going to define an event A in this sample space such that A intersection S is equal to what happens if A is having elements 1, 2, and sample space is having elements 1, 2, 3, 4. Then what is the intersection means? Common elements within these two are 1 and 2. This is nothing but event A. So A intersection S results to A. So now this, in place of sample space, I can replace this with, I know that here I'm writing A is nothing but A intersection S, and S I can write it as union of N is equal to 1 to capital N B N. So this is, and from this I can write N is equal to 1 to N A intersection B N. Next, if I take probability on both sides, if I want to find, why, because I am interested to find the mathematical expression of probability of an event A, that is P of A is equal to probability of union of N is equal to 1 to capital N A intersection Bn, right? So from third axiom, as I said, we are going to make use of an axioms. Third axiom of probability, this results, that is I'm telling you the statement, that is probability of union of all the elements or events is equal to, according to third axiom, is equal to summation of independent events. That is, here this union becomes summation n is equal to 1 to capital N P of A intersection Bn. So this is from third axiom, right? So in order to get clarification, please go through the third video of my PTSP course. It is probability introduced through axioms, right? So this is from third axiom. So we get this. So I'll replace this into the above expression. So P of A is equal to, at last you'll get summation n is equal to 1 to n P of A intersection Bn. And from joint probability, I know that P of A intersection Bn is equal to P of A given Bn into P of Bn. And this you substitute into this above expression. So finally you will get the mathematical expression for total probability theorem, that is equal to P of A is equal to N is equal to 1 to N P of A given Bn into P of Bn. So this is the final expression of total probability theorem. Right? I hope you understood this explanation. Right? So now we'll move to the next theorem, that is Bayes.
So whatever I has explained in the whiteboard, so I'm showing you in a one slide. It is a proof for total probability theorem. So please you can see this in one video. Sorry, you can watch this in one slide. So here in this, you can see whatever the proof I had done this for total probability theorem. So you Please go through this for 1 minute, or you can note down this proof in your notes so that it will be a reference for you when you are going for mid or external exams, right? So next we'll move to the next topic, Bayes theorem. So you all know, as I said, if you understand total probability theorem, it will be easy for you to understand Bayes theorem. The statement is almost same except the mathematical expression. So let us go through the statement. It states that if a sample space S has n mutually exclusive events Bn and n is equal to 1 to so on n, such that Bm intersection Bn is equal to 5 for m is equal to 1, 2, 3, so on n, and any event A is defined on the sample space, then the conditional probability of Bn and A can be expressed as. So if you just go through the statement of total probability theorem and if you compare with this Bayes theorem, so almost it is same, only the difference is there we are going to find only the probability of event A. Here I am going to find the probability of conditional probability of Bn, Bn and A, that can be expressed as mathematical expression is P of Bn given A is equal to P of A given Bn into P of Bn by, so denominator is nothing but total probability of event A. So let us go with the proof. See why I'm not making use of whiteboard is, so as you understood the total probability theorem, it will be easy for you to understand this proof. It is very simple and very important proof. So you can expect a long answer question, essay type question in mid and final exams, right? So let us consider examples. Just we are writing that given data that was mentioned in the statement. So sample spaces consists of n mutually exclusive events, and union of all this results to a sample space. So B1 union B2 union so on Pn, and A intersection S is gives, that is when I'm going to take intersection of A and S, so that results A, which is same as total probability theorem. Next, A intersection S, I can write it as union of all the events B1, B2, so on Bn. Next, A is equal to A intersection B1 union A intersection B2, so on A intersection Bn. Now I want to find the probability of A, that is P of A is equal to P of the right hand side, whatever the expression we are writing. So I know that from addition theorem, P of A union B is equal to P of A plus P of B. So I'm making use of this, and P of A I'm writing as P of A intersection B1 plus P of A intersection B2, so on P of A intersection Bn. Finally, I'm writing as summation P of A intersection Bn. And but from conditional probability theorem, I know that P of A intersection Bn, P of A given Bn is equal to P of A intersection Bn by P of Bn. So I hope you understand up to here. Next, I'll substitute this equation 2 into equation 1, which gives P of A is equal to P of A given Bn into P of Bn, right? Again, what I do is P of A I know, so P of A is nothing but summation of P of A given Bn into P of Bn. So if I'm going to substitute the equations 2 and 3 into equation 4, so that results the mathematical expression for Bayes theorem. I hope you understand this. If you haven't understood, please go through this video one more time so that you get clarity about Bayes theorem and total probability theorem. And uh, so this is about the two topics, total probability theorem and Bayes. So this is about the two topics. So for more videos, do like, share and subscribe to our channel, and with your cooperation or with your views, so it will be helpful for me to do more videos on this PTSP course. So thank you for watching.